When you solve a quadratic equation like x squared minus 2x plus 3 is equal to 0, which gives you complex solutions, in that case the solution to this would be equal to x equals 2 plus minus 2 squared minus 4 times 3 times 1, that divided by 2. This right here, 2 squared minus 12, this is just 12, so 2 squared minus 12 is equal to negative 8. The square root of negative 8 is equal to 2 square root of 2 times I. Put that in, you will get 2 square root of 2I plus minus is there, divided by 2. This gives you 1 plus minus square root of I. Now, if you try to plot that on an Argand diagram, so if your Argand diagram looked something like this, really roughly, so some sort of this, then the first solution, 1 plus square root of 2i, will look somewhere here. So this is the square root of 2 and this is 1. 1 minus square root of 2i would look exactly the same in length, but it will just go to negative of square root of 2. So what that means is this is a reflection of this complex number in the real axis. And what these are called, these complex numbers that are just reflections, are called the conjugates. The conjugate pair, or the conjugate of one complex number, is the other. So for instance, if you took the conjugate of 2 minus I, you are essentially taking its reflection across the real axis. 2 minus I would look somewhere here, let's say. So if this is 2 and this is I, this is negative 1, its reflection would be somewhere here, so 2 plus I. And the general scheme is that if you had a complex number, a plus I times b, its conjugate, if this was represented by z, its conjugate would be represented by z bar, and it would be equal to a minus ib. Just put, instead of the positive, just reverse the sign, make it negative. Now, conjugates of complex numbers are pretty useful when you're doing analysis, when you're trying to write proofs, or you're trying to write mathematical statements in general. So let's try thinking about some properties. So if you, let's say, took the conjugate of the conjugate, what would that mean? So you reflect something, you reflect, let's say this is your reflection, and then you reflect it back again. And since there is only one unique reflection that you can have, this will be just the same. So z bar is going to be equal to z itself. If you do that analytically, then you had a plus ib, let's say that was your z, then z bar will be equal to a minus ib. And z bar, that just change the sign again, so that will become z plus ib again. If you, let's say, added two complex numbers, so if you added z1 plus z2, what would be its conjugate? And you can work this out. So if you took z1 to be equal to a1 plus ib1, and z2 to be equal to a2 plus ib2, then its sum, the sum of these two, are going to be z1 plus z2 is equal to a1 plus a2 in the real part, and I times v1 plus b2. And if you took the conjugate of that, so you are just changing the sign that the imaginary part has, so instead of the plus, you put in a negative. If you had instead started out with z bar, so if you started out with z1 bar, then you would have got a1 minus ib1, and z2's conjugate will be a2 minus ib2. If you add these two, then you will again find the exact same expression. And since algebra gives you a general perspective of all the numbers there are, you can confidently say that the sum of these two complex numbers, z1 and z2, and then taken the conjugate of, will be equal to the sum of the conjugates. So the conjugate of the sum is equal to the sum of the conjugates. If you just placed a negative sign there, if you said what is the conjugate of the difference, well, since addition and subtraction are really closely related, you can say that the conjugate of the difference is the difference of the conjugates, and this will be something that you can do as an exercise. Instead of having the plus sign here, you could have started out with negative and would have gotten the same results. you can do this for multiplication and division as well. So if you took z1 and z2 and you divided them, what would be its conjugate? Well, its conjugate will be equal to the division of the answer that you get from the division of the conjugates of z1 and z2 if you instead had the product. So the product, the conjugate of the product is equal to the product of the conjugates. So it's a really nice distributive property, a distributive operation that you can do on complex numbers. But then you can use this to get a bit more mathematical definition of the real and imaginary parts of a complex number. Now, what do I mean by that? So if you had a complex number a plus ib, and then you couldn't write its conjugate for it, so that will be equal to a minus ib. If you added these two, so you added z times z bar, so z times z bar, that's equal to a plus ib times a minus ib. This is straightforward of the product of sums and differences. This is going to be equal to a squared minus the square of I and b. I squared is just -1, so that will just flip the sign and you will get a squared plus b squared. Notice that the magnitude of these two complex numbers, since they are just a reflection, they are going to be the same. And their magnitudes are actually equal to the square root of a squared plus b squared. That's something that we already know about. And a squared plus b squared, then we can write that as the square of the modulus or square of the magnitude of any of these complex numbers that you have. Either you put in z or you put in z bar. It really doesn't make a difference. So that's one property. You have z times z bar is equal to the square of the modulus of the complex number that you have. If you added these two complex numbers, what happens if you added z and z bar? That gives you that, since then the imaginary parts would cancel out, they are just the negatives of each other, this will give you 2a. Now a is the real part of z. So what that means is that you can write the real part of z as z plus z bar divided by 2. If you instead took the difference of z and z bar, so that will mean z and z bar, its difference, that is going to be equal to, well, you subtract out the real parts and you only are left with the imaginary part. So you get ib minus of negative ib. That gives you 2 times ib. So then what again, like the analogy from the real part, what you can do is you can say that b is the imaginary part of z. So I can write that the imaginary part of z is equal to z minus z bar, and you divide both sides by 2i. So you have the imaginary part of z is equal to z minus z bar divided by 2i. Now, these are some properties that I derived really quickly, and the purpose of this video was to just introduce them so that you are acquainted with the sort of algebra of complex numbers that we use in proving things. We will continue talking about complex numbers in the next videos.